Okay, good afternoon. Thanks everybody for joining in today. We have three speakers from ESnet who are going to be talking a little bit about data transfer node design patterns. This is the group that's been experimenting with and constructing a new generation of the data transfer nodes that we will be deploying on ESnet very soon, if not already. We have Charlie, Goran, and George. And they are going to be alternating back and forth on this presentation. And I'll toss it over to them to get started. So take it away, George.
Hey, everybody. So great to be here. And thanks for sharing your Friday with us. We're hoping to get a little bit back to basics. And part of this is, as Jason was mentioning, we're getting ready to deploy a few DTNs that may be of interest, kind of some showcase nodes. With this, we put together a quick slide. Don't hesitate to put your questions in chat. We're happy to take interruptions, and don't hesitate to just let us know as you have feedback. The slides, as you can say, were data transfer node design patterns. Charles, Goran, and myself will be giving this presentation. And let's see if I can get the slide to increment. There we go. And this is who we are. We're from Energy Sciences Network, ESnet. We're on the infrastructure team. We are 3 of 9. I'll give Charles and Goran a chance to say hi, who they are.
So I'm Charles Shiflett. I've been an engineer at ESnet now for about 6 months, so I'm fairly new to ESnet. I've been involved in file transfer now for about 10 years. So it started out as I thought a gigabit was fast, and as I learned out, that was not very fast. We hope to hit 200 gigabit file transfers sometime in the near future as we build out our network past 100 gigabit. Right now we're talking about our 40 gigabit DTNs, and we can talk a little bit about some of our 100 gigabit efforts as well. I will mostly be talking about the software side, and I'll probably get to that a little bit more when I get to part 3 of this talk. Go ahead, Goran.
Hi, folks. I'm Goran Pejovic. I'm part of the ESnet infrastructure team as well. I've been at ESnet for 5 years, a little bit over 5 years, and I've been involved with our previous generation of now slow 10 gig DTNs, and now helping Charles and George with our next gen DTNs. Later today, I'll say a few words on NIC tunings, what we do to our DTNs to tune the NICs, what our approaches are, and stuff around that. Thank you.
And I'm George Robb. Been playing with hardware for a while now. Know just a little bit about DTNs. It's all the basics. It's all the fundamentals. I'm so happy to be part of ESnet. I've been part of the community that I'm talking with for a long time now too. So I'm very happy to see so many familiar faces in the chat list. With that, we'll go ahead and get kicked off, and let's see if I can progress the slides. So today we're going to do our patterns. Our whole goal is to do pattern 1, which is basics of hardware, pattern 2, network placements, and pattern 3, software. Keep it nice and easy. Patterns usually show design issues by calling out missing pieces. A quick and easy example. These patterns, they look complex, but do something for that camera, take away the chassis, and you can see the flaw instantly. Same thing with bicycle, take away the frame or take away a tire. You notice that the pattern's not right. Similar, monitoring and baseline show patterns. I've tossed in a few graphs here. The one that's front and foremost is the My ESnet. You can see patterns that was taken earlier today. The green line shows a nice clean pattern of where some of our data is flowing to and from. A quick example of patterns that can show up in memory management. We see a nasty plateau. Nobody likes plateaus in their patterns. Temperatures, those look pretty stable. Stable can be a pattern too. Persona throughput tests, the spikes. Is it consistent? Is it spiky? Overall, enjoy your data. We'll be calling out monitoring and baselines quite often. Part of solving problems and seeing patterns is knowing your baselines. Pattern 1 that we're going to talk about, hardware. And in the scope of this, we're talking about what lives between the network cable and the humans. So the fun part, the servers, the data transfer nodes. And then I'm going to toss in a bonus pattern, pattern 0, the what and why, trying to keep things very basic. What's a data transfer node, right? It simply put is a data transfer node. We often get off into the weeds. We're always worried about, making it go as fast as possible or tune that last little bit of IO out of it. We often also forget, I personally do, that the purpose of the DTN is to serve science first. It's very easy to get lost in the weeds. It's very easy to get lost in file systems or RAID controllers or no RAID controllers or whatever we're trying to get done and get away from the core mission. A data transfer node is to get those data moved. It's designed and tuned to move that data. We're also trying to solve specific problems extremely well. So keep in mind as you're building your DTNs or deploying your DTNs or taking advantage of the science DMZ patterns, what is the problem you're solving? Don't lose sight of that. I know every now and then I will get off into the weeds and worry more about something that's not important for the overall big picture, and it can be a time-consuming effort. Outing to pattern 0, why do we have DTNs? You don't want it to compete with other resources. You don't want to waste time on a login node. You don't want to waste time on a web server. You don't want to waste time for anything when you're doing file movement or block movement or data movement. The Unix security philosophy, one purpose, do it well, do it very well, accept input, receive output. That also provides an excellent security posture. If you have a data transfer node that's trying to move files to and from, if it's a dedicated unified resource, think about the security wrapper that you can place around it. It becomes elegant, really easy. Monitoring becomes easy. Tuning network inhibitors becomes easy. Placement becomes easy. Another part about data transfer nodes is that it's kind of an agreement. We're saying that, hey, this node is dedicated to get the data point A to point B or point A to point Z. Get the data there. As long as you have the dedicated node, now your problem scope is very limited and easy to attain. Another fun part that DTNs can do, of course, translate and ship complex cluster attached storage, instrument-based storage. It can be scheduler controlled. You can put this behind Slurm or some other scheduler, and it can work very well if that's your design pattern. Pattern 1 that we're wanting to talk about is basically the good, fast, cheap, right? I tried building a quick graphic here. A few of you guys might know that network card or have used those. Yes, it is ISA-based. The whole point is we need to find a balance, right? It's for science. What's movable, what's tunable, what can be designed around? So the 3 elements that are easiest to work with on between the network cable and the human, CPU, storage, and network. Let's go. So let's start with CPU. Our balance that we're trying to attain here is clocks, cores, sockets. We can add in even more balance if you want to go to it for energy efficiency. What is the problem that you're being asked to solve? Or what is the problem you want to solve? Or what problem is now solved? What does that balance look like? How does that fit? So example being something as simple as threads versus flows. If you're single threaded, easy IO, a data transfer node can be very elementary. It can be a Raspberry Pi if you need it to be. It can be any scale that you need to go. You can have clusters of DTNs if necessary. But it's your problem and it's the problem that's being solved. What's the problem definition for it? Memory management, large versus small IO. That's another one where CPU and selection of CPU comes in. So one of the things that I'll ask out of the gates is, are your memory channels fully populated? Do you know how many memory controllers your selected processor has? This is a place where you're leaving performance on the table and it's an easy one to pick up, if not. Example being, in former life, I had asked vendors for the standard, I would like 128 gigs of RAM. That they'll happily cash your check and hand you 128 gigs of RAM. But is that balanced for the processor? There's times where you actually may have 8-channel processor capability. You may have 2-channel processor capability. Know your hardware, know your CPU. So basic question is a homework for the reader. Are the channels fully populated? There's other cases where data transfer nodes, you don't need a supercomputer. You don't need a $80,000 node. You just need something that gets the job done. I'm attaching up to an instrument. I need an OS that's this OS because it supports this instrument. I need to get that instrument data from point A to point B. That's a data transfer node. Tune it, make it the best node possible, give it a great security stance, place it properly on the network. It's doing its job. It solved the problem. It doesn't have to have racing stripes, although it is fun to put racing stripes on things. It can be cluster attached. It can have complex I/O. You could have massive parallel file systems on this side, your DTN or DTNs, and then your destination on the other side, which again could be another DTN going to clusters of file systems. It solves that particular purpose. The CPU decision for that becomes critical and important, right? Do you need to go multi-socket, single socket? Where are we going with this? Overall, it comes back to, once you've chosen a selection, get your monitoring, get your baselines, get your trends. Know what you're trying to solve and attain that goal. So next selection, let's go into storage. A balance that we're trying to attain here. We want speed versus capacity versus cost. What problem are we trying to hit? I'll harp on that. That is a pattern. And don't hesitate to think of RAM as part of the storage system. You can starve I/O by not having enough RAM. I can say maybe have too much RAM. Is it being utilized for the task at hand? Again, I'll just say, go check your channels. Are they fully populated? All flash technology. I was looking at an article today that was really impressive. They were talking about 64 terabytes on solid state. I mean, it might cost a small house, but the thought there being is it's 64 tera. It's a proof of concept. When some of the first flash drives came out, they were insanely expensive too. How much longer does spinning Rust have before we don't need it anymore? Or does it solve your problem and spinning Rust is exactly what you need? It's very difficult and complex to describe what a model storage is without knowing your problem statement. So it goes back to, what would be the best storage for your system? And don't forget about the RAM. And again, I'll call back monitorings with trends and baselines, right? That's the pattern. If it's starving RAM, up the RAM. If it's not enough capacity, you'll know pretty quick. And go from there. Don't forget to think about future too. Storage, again, we're going speed, capacity, and cost. I've harped on the same pattern of what problem is being solved. One of those problems that comes in complex, adds to the complexity, is if you're going to be using hardware RAID or not, right? There's some excellent technologies that allow you to not necessarily need a hardware RAID card, but are you putting in performance? Are you going for redundancy? HBAs can, RAID cards can be flipped over to HBA mode, and you can change out to just a bunch of disks if necessary. This adds a lot of performance tuning levers that you can go with. There's times where you need a simple, highly redundant, highly reliable data transfer node, and a RAID card is perfect for that. There's other times where you need a race car and you need to get that exotic I/O JBODed together via software-defined RAID array of some sort to put those JBODs into format, and let's drop the clutch and go. File system selections are another one that are really important. Know your limits on your file systems. There's a lot of defaults that are good, and I'll start by saying monitoring with trends and baselines. Is that file system meeting your needs and solving those performance issues? Like, is there a reason that you'd want to do something exotic like ZFS? Or is there something where, hey, ext4 works perfect? NTFS in certain cases. Are you attached to an instrument and this file system is accepted? File systems do have a lot of other fun characteristics too. Block sizes, stripe sizes, RAID levels. So keep in mind where your tuning is. And again, I don't want to prescribe something specific. It depends on the problem you're solving and the monitoring and baselines that you have in place. With the other components, we have hardware, interconnects, so network interface cards, right? In this picture, I've got well, probably several of the folks out there know that card very well. It's a 3COM 3C 900 multi-port. It's got the AUI, it's got the 10 base T, and it's also got that coax B and C connector. I might even have one of those in a box somewhere. I remember when that was a sought after card. Now it's like, again, we're dealing with speeds that are just intense. What problem are you solving? So do you truly need a terabit DTN? What will that do to your neighbors? Do you need just 40 gig? Do you just need 10 gig? Based on data, maybe a gigabit is plenty. Are you going cross campus, cross rack? Are you going cross continent, cross globe? Think about the problem you're trying to solve and how that network interconnect plays into it. Again, in this place, we're balancing bus speeds because we're trying to keep that card fed. We need the storage system to work in harmony with the CPU and the RAM to keep that data going onto the wire. Connection formats, are you going to use copper? Are you going to use optical? Are you on a wireless link for some weird reason? What needs to happen there? Can it tune? There's times when there's been network card selections that I've had and you have no knobs. You are given an OEM card. Here is one network card. I've also had cards where it's so untuned and so off the wall that it starts out as, say, an InfiniBand card, and you have to get into the firmware and bit flip it over to Ethernet and change things out so that it actually acts as a NIC. Now you get to start going from NIC tuning. Goran will have some things to talk on that here in a moment. Future proofing is another variable, right? So we start seeing articles talking about terabit. I saw one that was multi-terabit article. We talked about vendors that are dropping hardware that can do a single port that's 200 or 400 gig native. That's amazing. Is it truly needed? I mean, and this is where I personally can get lost in the weeds. I would love to have the biggest router, the biggest switch, the biggest interconnects, and I would love to have a DTN that's just completely smoking everybody just because. But downstream is an impact. Know your path. Cost functions, of course. I'm not going to go out and try and buy a terabit network card and expect it to be cheap today. That said, give it a couple of years, they may be commodity. It may be like us looking at that 3C509. Then also another option. This is something we found that's been incredibly useful. Tuning can be chasing a parked car, as I like to say. Pull over. I can't. I'm already pulled over. No, pull over more. Well, when you're trying to tune, sometimes if you overbuy your network card, you can self-cap your optics, and then it's easy. Let's say you have a 800 gigabit network card. It's easy to clip it down to 400, cap it at that interface if that's what the problem indicates. There's times where tuning a 10 gig card these days is just old shoe. It's easy. But again, I'll go back to, are you meeting the mission of science? Are you monitoring and baseline saying that you are meeting that mission? With that, no, this one goes there, that one goes there. I'll hand it off to Goran.
Thank you. Next slide, please. Okay, so now that we have, say we have our hardware figured out, we know what our needs are, the next challenge is to actually do the proper network placement for our DTN. So as our pattern suggests so far, first thing we would want to ask ourselves is what is the problem we are solving here? Where do we want to place this hardware, this nice shiny piece of metal we bought to transfer our data? And, first we got to ask ourselves if we are good network citizen, whether we don't want to put 100 gigabit DTN on a 100 gigabit pipe where other data is flowing that might saturate the link and not help us too much. So, working with network engineers and understanding what the network looks like, where we want to, what flows through the pipes we want to put our DTN in is very important. For example, on our 100 gig pipes, we are now deploying a 40 gig DTN with the future proofing George was talking about. When ESnet upgrades to a faster pipe, we'll be able to just flip the switch in software and make it 100 or 200 gigabit. Another thing we want to consider when placing a DTN on a network is what about congestion control? There are plenty of congestion control algorithms available. BBR is the most hyped one at the moment, I guess, and our engineers are actually testing BBR v2, and in near future, hopefully we'll be publishing some of the numbers on our knowledge base, fasterdata.es.net. Also, you know, when placing a node on the network, you wanna see how complex your data transfer is, whether it's a simple node-to-node communication or it requires more complex I/O of clusters talking to other clusters. So depending on that, you know, it can affect your tuning, or maybe there wouldn't be a need for tuning if you are doing a simple node-to-node, then, you know, it could work. And again, you know, monitoring is always, with transit baselines, it's always your friend, always keeping an eye what changes and how any change affected what's happening. A good example for a placement for a DTN was always Science DMZ. For folks who are not familiar with the Science DMZ, you have plenty of talks available on YouTube. If you just type that term, you'll find plenty of talks. But essentially what it is, it's like a DMZ sub-network that's not really trusted by the internal network that has a leg to the internet. And Science DMZ builds upon this model by, you know, optimizing for a specific task, whether that is like a high bandwidth and similarly. So, you know, this is a place where we would usually suggest placing a DTN to. Next slide, please.
So Goran, I'm going to pause you for 1 minute because I think we have two questions, or one question that came in that is relevant to what you just said. This is directed at George, but whoever wants to answer. Links to best practices for monitoring and baselines. Do you have any suggestions or anything that you could share?
Along the monitoring baseline, I would suggest your own personal data. Example being, what is your monitoring platform? Is there something that's taking in and doing basic graphing? Is there something that's, dare I say, a whiteboard in your office that you've written your peak or not? Just tracking it. I've seen some amazing science done and progress done from where you've saved a graph from many years ago and then look at the graph again and look at that same data and how you got that data. So best practices among monitoring and baselines is a complex thing, and it gets into data science. Basically, know your problem, know how to get the data, and know how to save and look at that data again. And a lot of monitoring systems will provide you with a lot of things. Example, in that graph, like the one where I shown the graphs, that's an open source monitoring system, Libra NMS. There was also the My Data, My ESnet on link that was showing graphs. It also has baselines and trends. And then there was another one that was a Grafana graph, and that also is a graphing engine that'll keep trends and let you know kind of what the feel is. Hopefully that answers the question.
Okay, and then we had one more come in as well. Interesting that you mentioned the hardware RAID and ZFS. Can hardware controllers compete with ZFS that has full power of dozens of CPU cores and tons of RAM on the main board?
That's an exquisite question. I love that question. Okay, so if we're trying to do ZFS natively, ZFS wants direct access to those drives. You want to get the RAID controller out of the way. ZFS replaces that in this particular case. When you're trying to compete with HBAs and how an HBA behaves with ZFS, you'll have to tune your system to the problem that's being done. I've seen systems that were able to saturate 40 gig lines that were exporting NFS of all things on a basic ZFS system that had only 2 controllers. What are you trying to solve is what I'll counter with that. And I love that question. I don't have an excellent answer for it. It depends on your problem.
Okay, we'll wait for that to be clarified. Andy wants to know, lots of things can poll and graph at 1 minute increments. Do you have any suggestions of monitoring systems that provide higher resolution, like 10 to 15 second cycles?
Yeah, that's a great question too. And Goran or Charles, don't hesitate to interrupt me or hop in too. So with Libre NMS, you can go sub-second. It depends on the resolution you're trying to solve. I've seen things where if you're trying to do things with SNMP, for example, you don't want to over-poll your devices. You could cause a hardship on that polling flow. If you're needing resolution of 10 to 15 second cycles, why is the need for that resolution? Is the burst that quick? The trend is more of what we'd want to go. That's a really good question, and I don't have a great answer for it, but I do know that you can go sub-second polling on a lot of commodity and open source monitoring processes and projects.
Okay, thank you. That was all the questions that we had for now, if Goran wants to continue.
Thank you, Jason. So back to the network. So now that we placed our DTN on a network segment and we are sure, we are not drowning the pipe, we settled on that. Now the fun begins. We actually start tuning the NIC. And tuning is a vast topic, and sometimes it takes a lot of back and forth to get what you really want, but it's worth the time. Usually, first question you want to ask yourself is what the problem is that you're solving. Sometimes, just getting the latest and greatest drivers, if you are having some simple node-to-node transfer, can solve all your issues, and there would be no need for like extra tuning. But if you have more complex environment, that might require some additional tuning. So some of the parameters, you can tune involve, changing the MTU, messing with the ring buffers, CPU pinning. We'll expand on this in a second. But it's important to remember to always do like one change at a time. That way you'll know what actually helped. If you make too many changes, and this has bitten us in the past, we make too many changes at once, you don't know what actually helped you when you are taking the measurement later on. While doing the tuning, I personally always like to use perf sonar in conjunction with GNU plot to actually make the plots, to take the baselines and compare with before and after. To me, it's like a manual kickoff, but it always, it works. It's simple enough to show me what the changes were at some point. If folks are interested, there's a script at GitHub that I can actually take iPerf3 data and plot it with GNU plots. I don't have it on hand, but if folks are interested, we'll be happy to share it afterwards. Next slide, please. Okay, so the things we usually look at when tuning the NIC for DTU is, one of the first thing is the MTU. I'm sure folks are aware what MTU is, but anyway, it stands for maximum transmission unit, and it represents the size of the largest data unit that can be communicated in a single transaction. Now, it's important to remember that if you are not connecting your data interface of your DTN directly to the router, but instead you are going through the switch, that you need to pay attention to the maximum frame size, which is like an MTU of a layer 2. So we are connecting our DTNs to the routers, but we noticed this with other use cases where layer 2 can actually drop our jumbo frames. And jumbo frames are basically very large frames with the large MTU. As I said, MTU is the largest data unit. It's represented in bytes. The maximum Ethernet size is 1500, but it can go up to 9,000 bytes for a jumbo frame. And it helps having one single data unit being bigger if we have a large pipe and we can push that. That usually doesn't work on a slower networks. Usually 1 gigabit plus is okay for jumbo frames. Once we nail the jumbo frames, see if that works. They don't have to be at 9,000. We can experiment. We can try 5,000 or something in between. That brings us to the ring buffers, and ring buffers, they represent, it's like a way to accumulate data before transmitting it, and storing it while receiving it, before passing it up to the stack. So each NIC has receive and transmit buffer sizes. You can actually see these with ETH tool. If you pass it -G, small g is to actually see what you have set up already configured. If you use capital, you can use that to set it up. Usually the regular desktop NICs have these buffer sizes small. They are also in bytes, and usually for desktops, they are like 256 or 512 bytes. But for high performance NICs, and that's usually what we do with DTNs, we usually go with 4 megabytes or maybe 8, depending on what our baseline show works better in our in our environment. And then once we configure the actual buffer sizes, we can mess with the large receive offload and large send offload, LRO and LSO. And basically what that does, it aggregates multiple incoming packets from a single stream into a larger buffer before they are passed higher up the stack. So this reduces the number of packets the CPU has to process, and thus saves the CPU time. There's a generalized version of LRO called GRO, generic receive offload, that is not restricted to TCP/IP specifically, but we like to play with both and get monitoring and baselines, see what helped and what didn't. Usually LRO is not operated on machines that are acting as routers, so this is like set up on a DTN only. LSO is essentially the same thing for sending. It's a technique of increasing outbound bandwidth and reducing the CPU overhead in a similar manner, just the direction is different. So the NIC in this case, when it's receiving, if LSO is enabled, the NIC will be the ones receiving the packets and splitting them up. You can actually access this settings for your NIC in Linux with ETH tool as well, with the K parameter. I believe the small k is to read what you have configured at the moment, and the capital K is to set your desired whether you want it on or off. These settings are basically set up in an on or off manner. We don't have any extra shenanigans there. And there's also a transmission queue length, which basically limits the number of packets in transmission queue in the interface device driver. Usually the default number for TX queue length is 1000. We like to increase that. Usually the number of 10,000 work for us. A lot of these baselines are on faster data, and as we are experimenting with our 40 gig DTNs, we will be publishing those as well. CPU pinning could be useful. For folks who are not familiar, it basically allows binding and unbinding a process or a thread to a specific processor or a range of processors. So what that allows is reusing, for example, the same cache. If a thread or a process was run on one CPU, and we can reuse the cache basically, and saving a CPU time, a little bit, not too much, a little bit. It can help. It depends, on our application. Usually the practical example of the affinity or pinning is executing multiple instances of an application that's not threaded on the same, so it utilizes the same cache. And you know, it's very important to remember while you're playing with these, you know, while you're twisting these knobs and tuning the NIC, when you reboot, in a lot of cases, you're not gonna save these unless you made a way to save them. So what we do usually, the simplest way with Linux is to utilize the etc local. You know, it's a config file which basically gets executed at the boot time. And this is where it ties in with the monitoring and baselines. Once our baselines show that we made an improvement with the knob we turned, we would basically record that in the rc.local file. So on the reboot that actually our Linux will set up everything, all our tunings that we need for our NIC. You don't have to use RC local. If there are other mechanisms on Linux, you know, basically to execute a shell script at boot time. That's our goal here. And that's what we are aiming for. And with that, I'm gonna hand it over to Charles, unless there are questions.
Yeah, we have a question here. This is a big parameter space. Do you find that all of these parameters improve, degrade throughput independently from one another, or are they dependent on one another in some cases?
I'll go ahead and answer that. So these parameters can be very complicated. So for instance, the buffer size on your Ethernet card. Having a long buffer in some cases can really improve things. In some cases, it can really hurt things. You have your cache, like now whenever you read data into a processor, it's not going through any intermediaries, it's going straight into the L3 cache. And so if you can keep everything in that L3 cache, that can be a really big benefit, but it's even better not to drop data or do these other things. So, you know, you really have to adjust each one individually and see if things improve. In some cases, you can have the whole set of your parameters adjusted incorrectly and have to make big changes, and then you'll start to see improvements. A really good starting place are things like the Mellanox auto-tune script if you're using Mellanox. Otherwise, you may want to look to the internet, even the faster data site, and see if it has some general, like, these are what we consider to be our best practices presently.
Okay, and then
oh,
go
sorry,
ahead.
I was going to add just a little tiny bit to that, saying that start with the big adjustment, the coarse adjustment hammer, and eventually you'll get down to the fine adjustment hammer. You can start with a big scope with MTU and talking with your network engineers, right? Ring buffers start getting into a fine tuning. CPU pinning, that gets more specific, and that looks at how your IO and your IO parameters are moving. TXQ length is sometimes a big knob to turn and an easy win. As a matter of fact, we saw TXQ length made a very large difference in our 40 gigs that we're getting ready to drop. And then sometimes the OS defaults, surprisingly, are okay. So there's times when we know better than the OS defaults, but there's other times where the baselines are okay to start. You know, the defaults are fine, but change one parameter at a time, record that change, fight forward.
And then there was one additional follow-up here, and I think this will probably dovetail with what Charles is going to talk about. Have you developed automation to explore the parameter space, or do you use intuition and manual changes to work your way through towards the faster throughput?
I feel like that's a better one for George or Goran to answer.
I'm not aware of our automations to explore the perimeter space. We usually, when we are placing DTNs, we work with our network engineers. You know, we are sysadmins. We work with our network engineers to get a better picture. That being said, we are building a next-gen network at ESnet. So I suspect those are automations like that would be an option.
Along the automation space, this is one of the reasons why a lot of interest in the BBR space has been put into place too. Something as simple as congestion control and congestion control algorithms can be a massive adjustment. Think about the old Reno versus HTTP or Cubic. I mean, there's a vast array of what happens when you get packet loss. So the thought there is automation towards that, and the automation towards just congestion control has made a pretty big impressive splash. I'll reference this forum. There was an excellent talk on BBR. I believe it was Neil. Rewatch that just for congestion control alone. And when we state that tuning is a vast, vast adventure, it is. And this is where I can definitely get lost in the mission of the science. And that's why I was trying to add into the scope. We could get lost in setting up machine learning and algorithms for just tuning the NIC. But is it getting data from point A to point B? Are your researchers happy? Are your PIs getting their data moved? Is it getting the data off the instrument? At one point, there's a slight amount of diminishing returns. That said, this is very fun, and this team assembled here, we really do love tuning DTNs and tuning hardware.
So yeah, with that said, I think let's go ahead and talk about the software problem. I think there's been some really big changes. I think starting with Sandy Bridge as a chip, like I actually really like the ISA chipset you had in there. Like back in the day when ISA is actually an 8-bit protocol that was upgraded at some point to be like 16-bit. And you used to like have to put an address on this bus that was shared with everything, and you would get back some data. And actually reading and writing to the network cards was a very slow and painful endeavor. Things have improved so much since then, where the processor has individual links to each component on the system. And at this point, we tend to think of our network card as being very, very fast. So we have all these really fast data. We then have the next problem, which is our software was designed around having sort of slower peripherals, and software hasn't caught up in some cases. So it is actually it is actually difficult to send data at 100 gigabits. And I hope with this talk, I can give you some of the ideas or some suggestions as to how to go about doing that quickly. So let's go ahead and start with the next slide that we have here. So I wanted to just point out that if you want to send data across the country, there's a lot of tools that tend to be very bad at this. And these are tools that we use on a daily basis. So SCP and FTP, for instance, just to name a few. So the first step you want to do is to try to define a baseline for what your system can do. On the network space, we have iPerf. iPerf is co-developed by ESnet. So there's two people on ESnet, John Duggan and Bruce Ma, who are trying to make iPerf be as work with all the latest options. And I certainly have not ever been able to find anything wrong with iPerf where I'm like, oh, I really want this option. No, it pretty much always exists. And if it doesn't exist, literally we'll add that feature, or someone on our team will. Not our team, but someone on the greater ESnet team. So iPerf is fantastic for getting that sort of baseline network performance. There's two tunings that you want to do with iPerf to get that baseline such that it is a real baseline and not a fake baseline. And that's within the kernel itself. You want to enable those large TCP windows. And then you want to tell iPerf to take advantage of those large TCP windows. And iPerf tries to be smart enough to use large TCP windows automatically, but you may want to specify that manually, just so it gives you feedback of like, I am actually using this large TCP window. And you can see, you may have to enable logging for that, but iPerf is really your friend on the network side. In the same way, FIO is your friend on the storage side. Jens Axbo is the person who is the primary developer for FIO. He also is the primary developer for the Linux kernel storage. So he's done a lot of Linux kernel storage stuff, along with the new U-ring addition to the Linux kernel, which allows you to do, in most cases, zero copy IO from whatever your storage is to whatever your userland application is. And I think that's a huge improvement, because for a long time, we never had a good way of filling up those storage buffers, especially when you read from a disk like a SSD. You can't just be like, I want to read a block of data. You have to actually, like, SSDs read best when you fully fill that read queue, which is going to require lots of individual read queues to be in there, not a single read queue as was the traditional, like, I'm reading from a spinning platter, where it's like this sequential pattern was king. Now it's really just keep those read queues full on the SSD, which means having multiple read requests at a time. And the cool thing with URing is because of the way it's designed, you can actually have very small read requests and still get good performance. So those FIO on the storage side, iPerf on the network side, that establishes your baseline. And then getting that combined baseline is a really difficult thing. For a long time, the combined standard that I used was actually tar CF, the files you want, going into something like LZ4 to compress it in a very light way, just because there's tends to be issues, if nothing else, with how tar compresses small files. So that brings that file size down a little bit. And then you can go out to netcat, which is a great way to just sort of go across the network without having any artificial congestion. That's basically opening a TCP port on one end, having it go to another end, and then doing the same thing at that remote end. And I had a picture of our excellent worker, the netcat, just so you can visualize computer, netcat, network. And that works great. So let's go ahead and go on to the next slide. So I just came up with some flow expectation numbers. So these aren't real numbers, but they should be good sort of baseline numbers of generally what you can expect when you start doing particular optimizations. So there's this really small number, which I don't think you can see. This is TCP over the WAN. If you just open a TCP connection from here to New York, I mean, it's far, but it's not even that far away. And we have this awesome network that is like amazing with 0 packet loss and really pretty low latency, all things considered. You're still going to get low throughput. And why is that? That's because without doing some basic optimization, specifically the TCP window, your throughput is just going to be awful. Once you tune for that TCP window and you do the other kernel modifications that were talked about earlier, you can expect to get pretty good throughput even without jumbo frames. And by pretty good, I mean like 10 to 15 gigabits per second per flow. So as a baseline, and there's going to be a lot of variation on that baseline, but good performance. Once you enable jumbo frames, there's a really nice jump up to the 40 gigabit region, and that should be the same across the LAN or across the WAN. And that per stream is about as good as we can get when we do a single flow or a single, sometimes even when I say a single flow, it's not quite true because you can have a flow that is worked across multiple cores, but a single core sending data, 40 gigabit, is right now your baseline. And then if you want to go even faster than that, you're looking at other technologies. I think the easiest way to do that is RDMA. And so RDMA, as opposed to the processor orchestrating, like, I want to read this data into the processor and then send it out onto a network card. RDMA is more like point through some software interface, point this thing at a buffer and have it send to another side. And in hardware, that happens really, really fast. And we can actually get single core performance at 100 or more gigabits per second per flow. The other way to do that, if you don't want to have this dedicated network and software stack, is you can use something like Intel DPDK. And then you're limited by how fast you can read and write data from memory to the network card. And it turns out that that, again, is pretty fast. But it may be that it's not actually that much faster than 40 gigabits per second, especially when you're doing anything other than just writing straight to the network card or reading straight from the network card. And of course, DPDK has the problem of you have to write a network stack to go along with that. And if you had any questions about that, I have written a network stack to go along with DPDK, so I can answer some questions there. And then the last thing on the receiver optimizations, you have the lower level things. I think just because of time, I won't cover those, but if you have any questions about that, feel free to ask after. And so this is sort of, okay, I'm sending on the network fast. What do I need to do on the storage side? And the storage side is almost always a problem. There's a lot of solutions that avoid this entirely. So if you're using Lustre or those sorts of solutions or GPFS, and you have a non-TCP backend, so i.e. InfiniBand, or the next generation technologies that are loosely based on InfiniBand. Those are designed so that you can have a clustered storage system. You pretty much don't worry about that. You just imagine it as being a cluster. And when you perform that read call, especially from InfiniBand, you're just going to have a buffer that magically fills up. It avoids the Linux VFS system. It goes straight into your application, and you can then send it out across the world if that is what you want to do. And those happen really, really, really fast. They're great. Less good is I have a RAID system. And when you start talking about a RAID system, this is typically going to be on computer, although you can also do something like Ceph, which is, instead of being on computer, it's a clustered storage solution, but that's going to be going in through your network stack and typically using the Linux VFS layer. And in those cases, you have to figure out how to read from those devices quickly. So when you read from those sorts of systems, you may follow some of the same baselines, which is I want to do a large IO size, which clustered storage typically always requires, but there may be additional constraints on that. Like you may want to read in direct mode, and direct mode is one of those things where conceptually, it's one of those magic bullets that lets us read straight from hardware and go straight into userland IO, assuming some constraints are met on the application space where things are page aligned, so on and so forth. But direct mode has meant a lot of things as it has evolved. Traditionally, traditionally direct mode just meant that a read from your application had actually been written to whatever device or vice versa, which meant that it could still be going through the Linux VFS layer, which meant it was still slow. It just gave you a guarantee on how that data was written. In the newer sense, that guarantee has changed to it is actually avoiding some of these Linux VFS layers. The modern approach to reading data correctly is 100% do it with uring. Uring allows you to have lots of concurrent requests happen at the same time and through sort of a zero copy architecture. However, uring tends not to necessarily be optimized yet to work quickly with the Linux software RAID, and or if we're using something different, like let's say Ceph, you may have the same incompatibilities, which means that you're going to fall back to reading large block size. And when you're doing that large block size, uring doesn't give you a huge performance improvement, and it may just be easier to use traditional POSIX IO. Hopefully that changes as the technology matures. And I just wanted to point out sort of like a traditional, or I shouldn't even say traditional, but this is like sort of a Sandy Bridge era, how do we go fast? And this is filling up our PCI Express lanes with NVMe-based devices and a bunch of network cards. So this is 440 gigabit network cards with a bunch of NVMe. And so this is like the 5 years ago approach to we want to go fast. And this was something that I worked on. Even though there's the really pretty 440 gigabit cards, I was never actually able to get 440 gigabit cards to work at the same time because I could never actually get 440 gigabit cards to like physically function together. And it gets to be really unpleasant to like pull out the right 40 gigabit card and replace it with one that works correctly. So I just figured out which of those 4 worked or which one didn't work. And so I was able to get 120 gigabits with this setup, which is still fast, but certainly not getting close to the 200 gigabit number that we now think that we can do with a single network card. Maybe asterisk, hopefully we have some time to talk about that. Let's go ahead and go to the next slide. So this slide is how do we actually hit that 100 gigabit speed on commodity hardware? And there's some asterisks to this, but the general approach is instead of doing it with a single flow is we do multiple flows. And we can actually do that with all of the things that you expect in a standard system. So we can use encryption through the new AES. Well, and when I say new, not really new since it came out with Sandy Bridge 9 or 10 years ago, but the new AES-NI encryption supports line rate up to some number that is well past our 100 gigabit level. So hopefully at some point we'll be able to say, this processor only works at some speed and oh, that's horrible. But right now that speed is we can do encryption at 100 gigabits per second, and that's fine so long as we use multiple threads to do that. So TCP flows, we can do that with lots of TCP flows, i.e. 3 TCP flows to hit 100 gigabit. Typically, it's easier for us to keep that as a multiple of 2. So I wouldn't ever recommend someone try to hit 100 gigabit with 3 flows, but with 4 flows, that's pretty easy. Even easier is 8 flows, and then you, within the flows, if there is storage IO latency, it kind of just gets hidden in the fact that some network flows are going to be a little bit faster and some network flows are a little bit slower. So there's a bunch of tools on faster data that you can investigate to try to support higher speed flows. The 2 that stood out to me are Grid FTP, which is mostly a Globus-based solution. And so that solution tends to be optimized to go fairly fast. BBC is another optimization that is available right now, where you can mostly send data across the network fairly quickly. We have our own tool that we've been using in-house, and I actually got the capitalization wrong on that. It should be capital E followed by capital S and then CP, and we expect that to be available hopefully at some point in the future. We're working with the science engagement team now, and ESCP is just a sister application to a DTN testing tool that we're also working with science engagement. And the idea of the DTN tool is to be able to test not just the benchmark in the network, but be able to test everything that you would expect in a network flow and benchmark that. And yeah, let's go ahead and go on to our next slide, which I think we might be at the end of our talk. So hopefully you guys have some questions for us, and hopefully that talk was exciting for you guys. It's really exciting for us to be able to present some of our work.
Well,
Yeah,
thanks.
absolutely. Thank you. Oh, sorry to interrupt.
Nope. I just wanted to thank all of you, all 3 of you. Really comprehensive overview, and thanks for taking the time to go into a lot of details on that. We did have one question that came in. Well, actually, we have 2 now, but I'll ask the first one first. How do you manage security with performance, which can be at odds with each other?
So there's 2 components to this. The first component is, at a high level, you need an architecture for how to allow high-speed flows. Like if you have a network where you basically have to SCP everywhere, you can do things where you can have SCP routing network traffic, and you can make SCP go faster with multiple flows, but it's a difficult problem to solve. Better is to use SCP or use Globus, which has some way of handling authentication in a way that isn't going to affect your flow. So one possible solution, and this is what we're doing with our not yet released application, ESCP, is you use SSH to initiate a flow between site A and site B, and then that does the authentication. Then you can transfer a secret key between the 2 sites and then use something like AES GCM to do the authentication of the flows. But that means that you're leaving the SSH tunnel and you need to establish some new tunnel, which means you have to work with your network team to enable some other port to do the transfer. And Globus is going to require the same, like you have to enable specific ports for Globus to speak quickly between hosts. And I think Globus has more of a defined architecture, whereas things like BBCP are going to be, we're going to spawn whatever our daemon is on the client and spawn something on the server and then expect that these ports are going to be open. And there still is security concern with this, even if you're saying I'm using encryption, you then want to say like what type of encryption or what type of standards. And right now the fastest encryption that's available isn't going to meet some of those FIP standards, for instance, just because those FIP standards tend to just take a lot longer to evolve, and there tends to be a lot more mechanism so that if you want to use like this new shiny tool, it's just not going to be available there.
I'll also echo out on faster data. We have security design patterns called the Science DMZ. Work with your network engineering team, see how your Science DMZ is holding up and behaving. There's a lot of touch points where you can even do IDS monitoring. 100 gigabit IDSs are not unheard of and should be attainable. So take a look at intrusion detection instead of network inhibitors or firewalls.
Okay. We had a couple more come in. The next one, mostly about status and cost of the various tools. So Globus has a cost associated with it if you use some of the freemium features. Of course, data transfer itself is still no cost using Globus Connect Personal. What are the licensures and or costs of BBCP and ESCP?
So the good thing is BBCP, which is available right now, is free, and Grid FTP, and for the most part, the transfer component of Globus is free as well. I think the premium features are more in the collaboration space, although I don't know the exact cost model for that. ESCP, when it finally does get released, will be released under an open source license. So long as open source equates to free for you, you're good to go there. There are issues with support for all of these tools. I think Globus is the only tool that offers support with it. BBCP is, I believe, is it Caltech or Slack that was spearheading that development? I forget offhand, but
I believe it was Slack.
Yeah, it is an academic effort with all of the pros and cons that entails.
Okay. Next one, it's more like what out of the box can ESP do, SNMP polling. Lots of stuff, unless you start changing code, only goes down to 1 minute. We're going to have to quit using an old software package called Snap at some point. Hopefully router telemetry and collectors will be flushed out by then. So that's a continuation of what you were talking about earlier, George. Any additional feedback on that?
I recall Snap as a replacement or a plugin in Libra that is called Weather Map. If I'm not mistaken, I think the spirit of this might be towards visualizations and like a dashboard for a radiator. There are solutions that are in that space, and it goes out to the number of pollers. But use caution when SNMP polling. You can overpoll. Try and get as specific to the MIB or ORID as possible, and then do one purpose well.
Okay. And last one that we have for now, any comments on data integrity and validation? Testing that others have done so far on Globus integrity checks show worse than 2 times performance impact. More specifically, is there a design pattern for integrity validation?
So this one gets a little bit complicated. I won't say like a lot complicated. So when you do encryption now, like with AES, with Galois counter mode, you do get a checksum that comes out of that. So you can encrypt data and have a guarantee that when you decrypt it, it matched whatever that block was. The problem is whenever you do a file transfer, your data integrity, when you do that, is only as good as I read a block and I believe that block is correct. And then when you write data at the remote end, I wrote data and I believe that block is correct. The reasons, when you start talking about data integrity within that flow, there's 2 types of data integrity that people want. Number one is they want sort of a more traditional, like SHA-1 type checksum. And the SHA-1 type checksums are actually slower than our encryption checksums presently. And so that just is going to require more processor usage per thread. You may be able to have a per block SHA-1 checksum and have everything still work. But when you have that checksum be multi-threaded, you somehow need to take all of these checksums that were generated that are multi-threaded and provide them into a single, like checksums are generally generated out of a single context. And that's a really hard thing to do. So you either say, I'm going to have some fancy parallel checksum, which I think like new object-oriented storage supports, or you come up with your new system. And within those software chains, I don't think someone has yet figured out like this is the standard data integrity checksum that we should use. So within a transfer, I don't think I have a good answer for you. There is also the school of thought, which is just reread the data a second time after you've done the transfer and generate a checksum, and then do the same thing on the receiver end. Obviously, that's going to slow down your performance quite a lot, but that's the only way to get something where you really trust this checksum and I really trust that checksum. In some cases, your storage system, like if you're using ZFS, can solve that for you. So you can actually do an in run, which is like pull your ZFS storage on this end and then pull your ZFS storage where it was written. And then you have an independent checksum that was part of your clustering solution. And I suppose when I said ZFS, that's sort of a lie. You could use things like Ceph as well, but whatever your storage provider is, GPFS, Lustre, those count as well.
Okay, and last one, if you're able to, do you have a link to ESCP yet, or is it still sort of running in stealth mode?
Yeah, we're still working with our science engagement team. So we don't even yet have a, this is when this will be available. It's just one of those things that we think that it will be available soon. And I wish that I had something better to say about that.
All right, well, when we have something better, we will certainly share it with everybody, Mark. So we'll let you know. That was it for questions. I'll put out the last call in case anybody has anything else. And while we're waiting for that, I'll thank you all three again. We will get the slides posted of this, and we'll make sure we get the video posted as well so that you can share this with others.
And again, thanks for having us, letting us be part of this, and thanks for sharing your Friday with us.
All right, well, thanks everybody. Just a reminder, we're not going to have a talk next week because of the holiday in the US. So we will pick up again on September 11th with Michael Sinatra, and he's going to be doing an overview of manners for routing. So I hope everybody has a good weekend and has a good holiday weekend next weekend, and we'll talk to y'all soon.
Thank you, everyone.